Good afternoon, everyone. What are the smallest battery and how we fabricate them here at Fraunhofer IZM? That will be my talk today. What we mean by small is just displayed here with our demonstrator, the B-carrying electronics. This is one of our smallest batteries with 2 solar cells on top to complete autonomous energy system. So I will give a short overview about microbatteries and the materials they are made of, in particular lithium-ion batteries. I will show you how we are fabricating them and doing also a lot of development on the material side and assembly of such small batteries. Then in the second section I will show the characteristics of the microbatteries and then at the end give an overview of possible applications. So the smallest batteries so far, these were the so-called thin-film solid-state batteries. They can be made very small in the millimeter range, and they're also fabricated on substrates like we are doing, like on silicon wafers or glass wafers. But the capacity of such batteries is very small because the thickness of the active battery material is maximum in the range of 10 micrometers. So the disadvantage here is the low capacity. Other small battery you may be all aware of are the coin cells and the so-called pouch cells. This is the technology used for any mobile phone batteries and a lot of other lithium-ion batteries. There is the smallest size is approximately 1 by 1 centimeter, which can be packaged in such a flexible bag. So in contrast to that, we are using a completely different technology. We are using silicon wafer fabrication, in particular the deep reactive ion etching, to make the housing for the batteries from silicon, and we are fabricating them on wafer levels of thousands of batteries at the same time. And the advantage over the thin film battery is that we can make the active material much thicker, so we're getting more capacity at the same footprint. The advantage of the silicon battery technology is that when we come to smaller size, then we maintain a relatively high overall energy density. Here are some examples of coin cells. If you reduce the volume from 1 cubic centimeter to a smaller size, then the energy density is reduced fast. And the thin film batteries anyway have a smaller energy density because the active layer are so small, but they also need a substrate and a housing, so they're overall smaller. And with our technology, due to the thin walls and thin bottom and lid, we can fabricate with silicon and also with glass. We can maintain relatively high energy density. And the improvement here is much more than due to new materials. This is also indicated here. We're working also on new materials with high energy density, so we can also increase in that direction. But the most important fact is that we get a certain capacity even at very small size. So there are many different electrode materials in the field of lithium-ion batteries. And we are also using quite a lot of them because they have all certain advantages for certain purposes. Here, this blue line is a typical one for lithium-ion batteries in the mobile phone or even for electric vehicles, starting at 4.2 volts. But there are also other chemistries. Maybe you're all aware of the lithium-ion phosphates, the so-called LFP batteries, which are safer and, for example, used for solar storage. One important electrode for us is the lithium titanate, LTU. This is used not as a positive electrode, but at the negative side. And then the total cell voltage is the difference of the negative and the positive. So the voltage is lower compared to the standard, where you're nearly at 0 volt for lithium metal, or typical graphite, you're only slightly above 0 volt. So you really come up with 4.2 volts maximum. But here we have only a differential voltage of maybe 2.5 volts. But this electrode has much advantages for our technology. So each electrode has its pros and cons. For us, the most important point is the specific energy, because the battery is so small, so we want to have at least a certain amount of capacity. So from that point of view, we're using the NCA as a lithium aluminum oxide material, as a cathode material, and also for most applications it's important the so-called C rate. This is a measure of the power, how fast you can charge and discharge the battery. This is the most important points. Lifespan may be, sometimes also a lot of cycles are required. But cost of material is absolutely no issue, and safety is also not of concern for such small batteries. Here again is an overview of the battery materials in the combination of anode and cathode. So here the LTO anode are the blue materials. So most used in our course is the NCA LTO combination. And in cases where also higher temperatures are important, we're using also LFP and LTO. But we're also working on all the other electrodes and try to optimize and adapt them to our technology. For the typical lithium-ion batteries, the NCA graphite combination, you have an energy density of approximately 700 watt-hours per liter. Just of the active materials, and now in new developments concerning the carbon with silicon on the anode side, you can increase the energy density. And also there is a lot of research ongoing for lithium metal battery and solid state electrolytes, but this is still in the research stage. And you can see here still a lot of improvement is possible if those materials can be made reality. We are also working on materials development. Here, this slide only showing examples, such electrode paste. We're using the same commercial material like for large batteries for the active oxides. But then such electrode not only consists of the active material, but also binder and carbon additives, which are required to achieve the electrical conductivity. And plotted here is the contact resistance to the aluminum current collector and the electrical conductivity of the electrode. So what's shown is here with an additive of carbon nanotube, you can increase the conductivity greatly, and you can also reduce the contact resistance. And then with the CNT, you can again then increase the amount of active material going back here. And with more active material, you get more capacity. But what is also visible on this graph is that regardless of the amount of carbon nanotubes and other variations, the biggest influence on the contact resistance is on the type of electrode, and the LTO is our anode material. And an aluminium, this has a too high contact resistance. This is a comparison to copper current collectors. This is lower, but to reduce cost of the microbattery, we try to use the same current collector for both cases, and we solved this problem by changing from aluminum to titanium current collector, and in this case the contact resistance is much lower. Another issue for our batteries is that they mostly are somehow integrated, and also during the fabrication process, the final encapsulation, a higher temperature is required. And most batteries perform maximum to 60 degrees for a certain time, but we need 90 to 110 degrees for several hours. Of course, it makes them also more user-friendly, because then later they can be also operated at higher temperatures. So we developed here together with an electrolyte manufacturer new types of electrolytes. And as you can see here, with the new electrolytes E1 and E3, we achieve much higher capacity at higher C rate. So C rate is how fast the battery is discharged. So at 1 C, the battery is discharged in 1 hour, and 10 C is discharged fast in 6 minutes. So here much improvements in terms of temperature stability with the new electrolytes. So, but this about the materials, and such development are done around the world everywhere. The specialty is that we are using the silicon wafer level technology as a housing for the batteries. For example, the through silicon wires can also be used as an hermetic feed-through for the electrical contacts. And the fabrication then goes as follows. In the clean room, on wafer level, such housing are made. So we have here side-by-side electrodes with very thin separation walls in between. Then metallic current collectors are fabricated. Also here for contacting pads, which can be interconnected with wire bonds. And when this bottom wafer is finished, then it is filled with the electrode materials for the plus and negative materials. This is done by microdispensing. Then a first lid is bonded onto the batteries, and this lid has 2 holes. Then they are filled with electrolytes. This is as well as sequential process with a microdispenser, which fills the required amount of electrolyte into each battery. And then we bond a second lid. This bonding of the lids is also done at wafer levels or at smaller pieces, but still with hundreds of batteries. Then we bond a thin glass lid and metallize the complete package, because the first and the second bond is done with adhesive, and we require a hermetic housing. So at the end we have a complete metallized battery housing. Another important process is the use of carrier wafers. We're using glass carriers. This is a special process which is well known for handling of thin wafers. But here in our case, it's not only because the wafers are very thin and the battery leads are thin, it's also important to have the lids already separated on a carrier, so that we can bond them all at the same time to the batteries, and then afterwards remove the carrier wafer. And with this technology, we can also fabricate batteries of any size, even round or whatever. So here's some pictures about filling the electrodes into the cavities. Here with such a dispensing system. And here we call it coupons. That are slices of the wafer which are fabricated at the same time, filling the electrodes, bonding the lids, and adding the electrolyte. Here this is a wafer with battery lids. And for this electrolyte filling, we need an argon environment, because the lithium is very reactive to humidity, but even for nitrogen. So we have such argon box system for the last steps of filling in the electrolyte and bonding the battery lid. So the batteries arriving from the clean room, and the first step is to dry them in a vacuum oven. Then we have a plasma cleaning of the bonding area, and then we bond the lid and fill the electrolyte into the batteries. So this is what the batteries are looking after final metallization. This is a step where we metallize. This is done first by sputtering and then electroplating a thicker nickel layer, which is shown here. And you see also here, separated from this nickel layer are the wire bond pads. So this requires still lithography and is quite an effort. And because we have also quite great height levels here, and it also requires some temperature. So it's important that the materials are stable under those temperatures. All in all, we have two slightly different technologies. One is for the very small batteries in the size up to 1 or 2 millimeters and thickness up to maximum half or quarter of a millimeter, and slightly larger batteries in the millimeter size. So here in the range up to 200 microampere hours, and we can go up to 1 to 4 milliampere hours. We also made a cost estimation of those batteries. If we are using a relatively large run of 25 wafers of 200 millimeter wafers, then we can really produce some 100,000 batteries on such a run if they are very small. But if the batteries are larger, here in the 10 square millimeters range, then we end up in of course of several euros. So that's of course much more cost expensive compared to coin cells, but there are many applications where it's possible to use batteries of that pricing, in particular in the medical field. So after fabrication, we have 100% testing of the microbatteries in such a probe station. We have still some problems with scattering of the parameters. Here the slide shows the scattering of capacity of 180 batteries. So in the end, we sorting out all the batteries which fulfill not the requirements, but we are also working on this problem. Is that a bit to do with the wetting of the electrolyte and maybe also with the contact resistance. So some more slides about characteristics. The batteries with the LTO anode has a discharge voltage in this range between 2.5 and 1.8 volt. We also test them with pulse discharge as shown here for pulse heights between 30 and 130 microamps, and they also perform well. We can also cycle the batteries here shown 800, nearly 900 cycles. But this is similar to larger batteries if you use the same materials. On the right side here is a capacity as function of the discharge current. It is visible here that with the LFP cathode we achieve higher currents compared to the NCA, but this was before we changed to new current collectors. Maybe if we get in the future also higher current stabilities of the NCA LTO batteries. One important feature for many autonomous sensor application is the deep discharge behavior, because sometimes you do not know how long the battery is stored without any recharging. And so we made a special test here to short circuit the battery at 0 voltage for 100 of hours, and then cycled again and measured the capacity and the internal resistance. This is compared here at the right side with a traditional battery with carbon graphite anode compared to the LTO. So you can see we have also slight degradation of capacity depending on the hours at 0 voltage, but much better performance compared to the standard battery chemistry. And here also the impedance is also increasing, but much less compared to the state of the art. Self-discharge is also an important feature. We tested here some for 14 days and for 4 months. And there was no detectable degradation during 4 months. And we had some self-discharge for those tests, but some of the cells have no self-discharge. Some have approximately 20%. We also still have to figure out what is the reason. Maybe some pinholes in the passivation of the silicon. But for most applications where we have frequent recharging by energy harvest or whatever, even 20% per month is not such a big issue. So this was short about the characteristics. Now I will show you some applications for our small batteries. Here, this is a project funded by the German Ministry of Agriculture, in particular for bee research. And an advantage of the silicon housing is here that the battery is so lightweight, so we can get the required capacity of 24 microampere hours with a 2 milligram battery, and also an acceptable size for that beam that they can carry. So just to give you an impression, the bee can carry 60 milligrams maximum, and they're unaffected in behavior up to an additional weight of 10 milligrams, because together with the complete electronic module, the limit is then 10 milligrams. There's another example. This is a project of the University of Michigan. They're making research on that monarch butterfly, and they're using such a stack of ultra low power chips for the electronics, but they do not have our batteries, and so they stack 3 thin film batteries, which is shown here at the bottom. And the weight is also of all those 3 batteries in such a range of 2 milligrams. Another interesting project is for special micro hearing aids. There is this company Vibrosonic here in Germany, which built a special piezo actuator which directly stimulates the air drum. And in the next generation product of this company, they want to combine all in a so-called hearing aid, which directly sits here on the eardrum. And for that purpose, we developed also a battery which fits here. And the requirement was here a total capacity of 700 microampere hours. That's the lifetime of the battery is 12 hours. The recharging here is done with infrared diodes, and there are solar cells on the module top to recharge it. And this was a big requirement for fast charging, for better, for user-friendly systems. You want not to charge all the night, but maybe in half an hour or so maximum. For an optical application in the medical field, we developed such very thin and long batteries. We used here a bit different packaging technology with silicon, through silicon feed-throughs. And this, we used here also a bio-friendly electrolyte for this application. Somehow a similar application I've found on the internet. Here's a Mocho Vision system. They developed their own battery, shown here. So to have a complete display in the eye glass lens. So very interesting thing. So, but it's a bit, I think, also something for the future. But maybe an application for such small batteries. They also have here a medical grade micro battery developed. Yeah, and what could also be applications of such small batteries, for example, to increase the maximum reading distance of RFID transponders. This is shown here. They combined it with a supercapacitor shown here, and they could increase the distance to 25 meters with this additional power from this capacitor. And in case of very large volume constraints, so if it have to be very small, then you could also use one of our microbatteries and make it then smaller compared to this capacitor. Here's another example also of such a RFID wireless sensor system. Here with a patch antenna, and they use here also this era for solar cells for recharge, and increased with the help of this additional power the reading range to 27 meters compared to 12 meters without this energy source. And yeah, here, so the maximum current here is 230 microamps per megahertz. I think this is the upper range of our batteries. Better would be a bit less, but this is an interesting range anyway for our microbatteries. So, and to end up, what could be the future development to make a complete system in a package where the battery, for example, because the battery maybe will the largest component, can be at the same time used as a substrate with a redistribution layer, which then interconnects electronic chips and components. This is possible for our technology, giving more advantage of this relatively expensive battery housing. But this is something that can be done with our technology if things must be very, very small. So to summarize, imagine new applications, in particular in the medical field, require very small batteries. For example, these tiny data loggers or battery-assisted RFID. Much higher energy density compared to thin-film batteries can be achieved with our technology. And we developed a lot of processes and special equipment for prototype fabrication of such small batteries. And we are able to fabricate prototypes up to, say, several thousand batteries with our equipment and with our technology. Of course, for larger markets, there is a next step required in cooperation with the battery manufacturer to scale up this technology. So, thank you for your attention.